Hello everyone and welcome to this fifth lecture of the course Solar Photovoltaic System Design. So today we will continue our discussion on solar radiation components and then also look at a very interesting concept of typical meteorological year. So in the last lecture we talked about the three components of radiation: the direct normal irradiation, the diffuse horizontal irradiation and the global horizontal irradiation. So we will start the today's lecture by looking at the instruments which are used for measuring the three components of these radiations. So to begin with, let us look at this particular device. Can you make a guess what's the name of this device? Yes, this is known as the pyrheliometer. So this pyrheliometer is used for measuring the DNI component of radiation or the direct normal irradiation component. If you recall our discussion in the last lecture, we talked about it that DNI is the beam component, and as the name indicates, it is measured on a surface perpendicular to the direction of the beam component. That is why the name direct normal irradiation. So this particular thing is measured on a surface which is perpendicular to the direction of the radiation. Now the question arises that how does this particular thing work? How do we ensure that we are only capturing the direct normal irradiation? So in this tube like structure which you see here, I will draw a similar thing here. So what we have is that at the base of this tube you have the sensor which senses the radiation, and at the top you have a particular aperture here through which the radiation is allowed to go inside the tube. And this aperture, let us say if you look at the entire sky hemisphere, so this is the entire sky hemisphere, and this is, as we understand, this is 180-degree field of view. So this particular device is designed in such a way that this has only hardly a 5-degree angle of view. So out of the entire 180-degree of the sky, only a 5-degree opening is here. So this field of view of this device is hardly 5 degrees. So that means that only the beam component of the radiation, the one which is coming directly from the sun, only that can enter. Even if there is some little diffuse radiation at the surface here around the aperture, it will sort of get absorbed in the upper region of the tube, and only the beam radiation reaches the sensor at the base of the tube. So that is the idea. We are only allowing the beam radiation or the direct radiation to reach the sensor which is at the bottom of the tube, and this particular sensor then measures the intensity of this radiation. Now the question arises that sun is not a static thing, it is continuously moving. I mean, earth is moving around the sun, but if you look at a geocentric perspective for an observer on the earth, the sun seems to be moving continuously from east to west in the sky. So for that matter, this particular device cannot also be a static device. It is not possible to measure DNI through a static device. It has to track the sun throughout the day. So therefore this particular tube has to have a tracking mechanism from east to west direction as the sun goes. So in this figure, if you see here, this particular thing will have a tracking mechanism, and the tube will track the motion of the sun from the east, the sun rising in the east, it will go from the east to the west as the sun moves. The tracking would be there. So that is the daily tracking. East to west, as you understand, is the movement of the sun over the day, but across the year there is some north to south movement also. And to understand that in a brief manner, suppose for an observer in the northern hemisphere, let us say this is the location where we are interested, and this is the due north, this is due south, this one here is the west direction, and this one here is the east direction. So as we understand, the sun rises in the east and goes to the west. But if you are in the northern hemisphere, and suppose a typical example we take, let us say you are at the Tropic of Cancer. So for an observer at a Tropic of Cancer, this east to west motion of the sun will always happen towards the south. So basically what I mean to say is that the trajectory of the sun would be something like that, rising in the east, going to the west, but somewhat towards that particular curvature, that arc will be towards due south. And only on one day, when the summer solstice is there, for the observer on the Tropic of Cancer, this movement of sun from east to west will be directly overhead. The sun will be going in directly overhead, 90 degree above that particular observer. For all the other days, this movement will be due south. So the basically the slope of this arch which the sun carves in the sky from east to west, that slope will keep on changing throughout the year, but it will always be towards due south. So what that means is that for in terms of our measurement of DNI, that for pyrheliometer, this tube, as we said, must move from east to west on a daily basis, but then the angle at which the tube is oriented, that needs to be adjusted on a daily basis across the year. And that is why you see this other arm of the pyrheliometer. So this can move in a perpendicular direction to that of the motion of the tube, and this, the tilt of the broader arm of the mechanism, that captures this north to south motion of the sun for an observer on the earth. So that is how, so basically this has got a 2-axis tracking. First axis of tracking is east to west on a daily basis, and second axis of tracking is north to south. So we have east west tracking on a daily basis, and then the north south tracking over the year. So let us say for an observer in the northern hemisphere seated at the Tropic of Cancer, the maximum the sun will come to northward for him will be on the summer solstice on June 21. Then gradually the sun will start going southwards, so to say, and the southernmost point for the sun would be on the winter solstice, which is December 21. And then again from December to June, the relative motion of the sun is towards the north. Basically, the east to west arches which the sun traces in the sky, they become more northward towards June, and they become more southward as we go towards December. So that same principle is used for the pyrheliometer, and dual axis tracking is there, through which we can measure the DNI across a day and then across the year. So this is the pyrheliometer. Then another instrument in this regard is this one. Any guesses for this name of this one? Yes, this is known as the pyranometer. This is a relatively simpler instrument as compared to pyrheliometer. So this is used for measuring the GHI, or the global horizontal irradiation. As you can see in this figure, it is just a static device which just sits at one place. There is no tracking involved here, no complexity of that sort. It is, so here just at the base of this glass dome you have the sensor. So you have the sensor here, and then there is this glass dome on top of this to protect it from the atmospheric interferences of water or wind or other things. And then you can see, as you can expect, the solar radiation will be falling from all directions. So you have a pyranometer seated here, and it is getting radiation from all sides. So you are having the beam radiation, you are having the diffuse radiation, all those components are there. So this particular device will capture both the DNI and as well as the DHI. So DNI cos theta z plus DHI, the entire thing it will be able to capture as the sun moves across the sky, because it is just sitting at one place. So it is just capturing the GHI throughout the day. So an unshaded pyranometer, open pyranometer, this can be used for GHI measurement, relatively simpler. And then the third one is this one. This is again a pyranometer, but there is a twist to it. There is, this pyranometer is there with a shading ring. So as you can see, there is this shading ring here, this black ring around the pyranometer. So you have this pyranometer here. This is the same unshaded pyranometer which is there in for GHI measurement. But now on top of this pyranometer, you can see there is this shading ring which has been mounted. So this one is what we call as the shading ring. And you can say that this is just the opposite of the pyrheliometer, in the sense that the pyrheliometer was tracking the movement of the sun from east to west, and the aperture was made so small that only the beam component or the direct component could reach the sensor. Now this one here, this is measuring the DHI, or the diffused horizontal irradiation. So here we just need the opposite of a pyrheliometer. That means we need to cut out the beam component or the direct component. Everything else is welcome. So that is what the function of the shading ring is there. So again, this shading ring, if you were to draw this angle subtended by the shading ring to the sensor, this would again be that same 5-degree angle, and the orientation of the shading ring would be in such a way that, let's say if this is east and this is west, and as the sun goes from east to west, for the entire day the shading ring will block the beam component or direct component from reaching the sensor. Only the diffused radiation will be reaching the sensor throughout the day. So instead of tracking, we don't need a tracking mechanism here, it is just a static sensor, and the shading ring orientation is adjusted in such a way that on a given day, as the sun goes from east to west, throughout the day the beam component is cut off from the sensor, only the diffused radiation is reaching. And then you may ask, what about the north to south movement of the sun, because east to west is on a daily basis. Then north to south movement, as we discussed just now, there is a north to south movement for an observer on the earth. So for that, what we need to do is that we need to adjust the angle of the shading ring. So this tilt angle, as you can see here, if this is the tilt angle of the shading ring, so this angle needs to be changed on a daily basis. It can be programmed, it need not be done manually. So it can be programmed with a motor supply and a controller, that the tilt angle of the shading ring would change on a daily basis. So if we are an observer in the northern hemisphere, and as we move from December to June, the shading ring would gradually be needed to made more northwards or more vertical. And as the sun moves from June to December, gradually the shading ring would be needed to be more tilted or more southwards. So that way it can be programmed, and the tilt angle of the shading ring needs to be adjusted on a daily basis, whereas on a given day there is no tracking needed, just the shading ring circumference or the ring is designed in such a way that it just blocks the beam component of the radiation from reaching the sensor. So that is how we measure the DHI. So those are the three instruments which are used for measuring the three components of radiation. And as we discussed earlier, that out of these three we only need to measure any two. So which one should we measure? What is your preference? What would you say if I were to give you a choice? So having looked at the descriptions of these equipments, I think the obvious choice would be, first choice would be GHI, the simplest one. Just you place an unshaded pyranometer in the open, it measures the GHI. And probably the second choice would be DHI, because it is relatively simpler. It just have a shading ring, and the shading ring angle needs to be adjusted on a daily basis. Whereas the third preference would be the DNI. DNI is the most complicated pyrheliometer. As we saw, it is a much complicated machine and has got 2-axis tracking. So we can measure just the GHI and DHI, and we can find out the third one. And at this point, I should also mention, for your information, that in fact there are a family of models, mathematical models, what are known as decomposition models, which can make our life even simpler. So these decomposition models are designed in such a way that if you give them the GHI as the input, they can tell you what will be the DNI and DHI. Of course, along with the latitude of the place, the time of the day, and the day of the year. So if you inform these particular variables to these decomposition models, then they can decompose the GHI into DNI and DHI. So in fact, if we just measure GHI, then also, it will not be 100% accurate, but to a fair degree of accuracy, the decomposition models can give us the breakup of DNI and DHI. So in fact, just measuring one would also do. Even if we don't measure DHI, still to a reasonable degree of accuracy, we can get the solar irradiation components. And that is why usually across the globe, the most popular measurements are for GHI, and second most popular is DHI. DNI is very rare. Only some very sophisticated laboratories, they usually measure the DNI on a regular basis. So that is about the three components of radiation and their measurement. Now I am showing you this particular graph, having discussed the three components in quite a bit of detail. It would be interesting to look at this particular graph. So as you can see here, there are three curves shown on this particular set of axes, A, B and C. And any guesses which one is which component of radiation? Yes, it's a very easy thing to guess, because especially if you look at the equipment pictures given there, A, B and C, then the answer is a giveaway. So as you can see, the equipment A, the equipment shown in figure A, that is basically a pyrheliometer, and therefore the black curve is what gives you the DNI. Then the equipment given in the figure B, that is pyranometer, an unshaded pyranometer placed in the open, and that is what is giving you the GHI. So the orange curve is the GHI, and the C figure, that represents a shaded pyranometer. So therefore that is giving you the DHI component. So those are the three components of radiation at a given location in USA, Golden, Colorado. This image is from the National Renewable Energy Laboratory data. So these are the three components. But one very interesting thing is there, if you notice at the below the graph. So you have this graph in irradiation, irradiance versus the time, and then below you have the sky images. So that is something very important and interesting at this point of time. We should understand what is the impact of clouds on the solar irradiation, and you'll see, you'll be in fact very amazed to know that this is like the most important factor which determines the different components of radiation. If you look at these sky images below the graph, so early morning 8 a.m. you see there is a very clear sky. So these sky images are captured by something known as the fish eye cameras or the sky imaging cameras. And if you look at the, if you just look at the shape of the image, it looks like a eye of a fish. That's why the name fish eye camera. So if you look at the 8 a.m. image, the entire sky is completely clear. It's like a typical clear sky condition. There is no speck of cloud there, and that is what you see in the graph. The black curve is soaring up early in the morning and going up to a very high value pretty early in the morning. Because there is no cloud cover, the direct normal irradiation is coming to its full extent within a few early hours of the morning. Then gradually, as we move from 8 a.m. to around 12 noon, as you can see here in the second image, at the fringe there are some clouds which are forming. So at the fringe of this particular image, you can see there are some clouds which have started to form, but still there is nothing around the sun. The sun is completely clear, and clear beam radiation is coming from the sun. Therefore you see DNI is still at a very high value. So DNI, as we see here, is it's at a pretty high value, whereas there is some diffuse radiation. The blue curve has also picked up little bit, and there is some little diffuse radiation which is there, the blue curve is there. But the most interesting thing happens later, when around 2 p.m. if you see that the third image, now the sky is almost completely overcast. There is only a very little sky which is visible on one side, but the clouds, they are very dense at this point of time. The optical density of the clouds is very high, and they have completely covered the sun disk. So we cannot really tell that within this particular cloud cover where the sun is located and what is its intensity. There is no way of telling that, and that is what is shown here in the graphs. If you see that the black curve is sort of fluctuating initially and then coming down and hitting 0 at this particular point of time. So the direct normal irradiation is completely cut off because the sun is completely covered by the clouds. And at this point of time, interesting to note that the diffuse radiation has increased in quantum. So it has come around 200 watt per meter square, but that is like, hardly 200, 300, at max 400 watt per meter square is what the diffused can go up to. It can never go to 800 or 1000 watt per meter square. And at this point of time, as you can see, the orange curve and the blue curve are overlapping. So entire GHI is nothing but DHI at this particular point of time. Only DHI is there. DNI is completely cut off. So GHI is same as DHI around this time. And then gradually, as we move further in the day, around 3:30, 4 p.m, you can see the clouds have sort of scattered a little bit. There is still a very high degree of cloud cover in the sky, but the sun disk is sort of visible, though there are clouds, in the vicinity of the sun disk. So that is what is shown in this graph here. You can see the black line is back, the DNI is there, but it is fluctuating, due to the clouds are moving. Clouds are also not a stationary phenomena, they are moving cloud fronts. So, there is a fluctuation in DNI. And GHI is also pretty high at this point of time because there is a very significant amount of cloud cover across the sky. So that is why GHI is also there in the range of 200 to 400 watt per meter square. DHI is there, and then with DHI and DNI, the overall GHI is there in the orange color there. And then gradually, as the day proceeds, both these radiations, they gradually die out, and there is a sunset time there. So what this graph tells us very interestingly is that the cloud cover is a very, very important phenomena if we want to understand the solar radiation. And somehow the fact remains that clouds are not so easy to predict. So they are pretty uncertain in nature, especially in some particular seasons like the rainy season, the monsoon season. There is a very high degree of cloud cover, and also there is a lot of uncertainty when the clouds will be coming and going. Also, in different geographies, the extent of cloud cover keeps on changing. So there are coastal areas when during the afternoon time usually the clouds will be there. So wherever there is a lot of cloud cover or the clouds are very frequent, there the solar radiation uncertainty would be much higher. But if you have a location where there is a clear sky condition type of situation, there the solar radiation would be very much predictable. So the complexity in the fluctuations and variability of solar radiation is mainly due to the cloud cover which is coming, and also some local phenomena that, like, there can be aerosols or particulate matter or pollutants in the local atmosphere which can cause that phenomena. So moving ahead, there is one more particular concept of solar radiation which we should be aware of, which is very similar but still a little different, that is known as solar insolation. So far we have been talking about solar irradiation or irradiance, and when we talked about solar irradiance, we looked at the three components of radiation as well. We looked at the DNI, we looked at the DHI, and also at the GHI. And all these three we saw they are being measured in the units of watt per meter square or the incident power density per unit area. So that is the standard way for measuring solar irradiance. But there is another analogous term which you should be aware of at this point, which is known as the solar insolation. So this is little different from the solar irradiation. It's very analogous but slightly different. So let's define it first. The solar insolation is the total amount of solar energy received at a particular location during a specified time period. So when you are talking about the solar insolation, we are saying it is the total amount of solar energy received at a particular location during a specified time period. So basically, in this watt per meter square, if we multiply it with units of time in the numerator and the denominator both. So some examples of this can be like the total kilowatt hour per meter square per day, or the total megajoules per meter square per year, something like that. So this is the daily insolation. How much is the total energy which is incident on a unit area So this is the total amount of energy which is incident on a unit area over a period of day. This is like the annual insolation. The total amount of energy which is incident on a unit area in the entire year. So like that we can define daily, monthly, annual, weekly, different type of solar insolations, and we understand that this is basically the energy over a unit area over that particular time period. Also, if you look at it graphically, when we say solar irradiation or solar irradiance, then we would have something like this, a variation like on a given day going up and gradually peaking, then coming down, then night time it is 0, and then next day it going up again and having some fluctuation and then going down, and like that that would be the solar irradiance graph if I were to plot it in watt per meter square against the time. And then the solar insolation would be nothing but the area beneath this curve. So, this is the area under this curve is the solar insolation. How much is the energy which is incident on a unit area in a given period of time, usually measured on a daily basis or monthly or annual basis. So, solar insolation is also many times used for solar PV calculations, and these two have they are very analogous, very similar, but they have distinct applications. So, if let us say I want to do the overall sizing of a system. So, suppose I want to do the PV system sizing based on energy balance only. That means that the total energy requirement which I am having for a particular application, I need to get that entire energy from the solar PV system. So, for that type of study, solar insolation is good enough. If I just have the insolation value, that how much is the daily insolation or annual insolation, that can help me do the PV system sizing based on the energy balance. But if let us say I want to do some other more detailed studies. So, suppose I want to study the PV system performance on hourly basis, and let us say I want to look at the profile of power or voltage or current output of PV on hourly basis or sub hourly basis, then for these type of studies we will definitely need to go for solar irradiance. We will need the time to time fluctuation of the power intensity of the sun. So, depending on the application, we can use solar insolation or solar irradiance for different types of studies. So, this can be for hourly or also the even lesser sub hourly studies. And now this solar insolation, because we talked about it, let us look a little bit about how it is measured. So, we looked at solar irradiance, and by the way, before we go to the measuring device for solar insolation, we also should understand both of these are interrelatable. So, if I know the solar irradiance, I can definitely derive the solar insolation, right, because both are similar. So, we have watt per meter square for solar irradiance, and then if I multiply it with time units on the numerator and denominator and then do the integration, I get the solar insolation. So, they are interrelated. They can, if we know one, the other can be derived, but then if we want to measure it separately, solar insolation, then there are dedicated instruments for that as well, which are not very popular these days, but used to be popular historically before so much development in the measurement and sensor technology. So, this is what is used for solar insolation measurement. This is known as a Campbell Stokes recorder, and this Campbell Stokes recorder was traditionally historically used for solar insolation measurement. And here, as you can see, there is this crystal ball type of structure. So, this crystal ball typically of 10 centimeter or 4 inches in diameter, and it is designed to focus the rays from the sun onto a card mounted at the back. So, as you can see here, just behind at the base of this crystal ball, where the crystal ball is mounted, you have this, this metallic arc type of thing. And in this metallic arc, if you focus, there is a scale here, and then there is aperture in the middle of that metallic arc. So, this particular thing, has a structure where inside this metallic plate you can put some special sunshine recorders. There are specialized cards which are placed in the grooves inside the metallic plate, and then the sunshine recorder, the crystal ball, it focuses the sunshine to this aperture opening, and depending upon the intensity of solar radiation falling on those cards, the cards are burned to different extents, and they are calibrated in such a way that the extent of burning of the card can give you the reading for the amount of solar energy incident at that particular point of time. So, from that we can measure the solar insolation. So, this is how we can measure the solar insolation using the Campbell Stokes recorder. So, today we looked at the measurement techniques for different types of solar irradiation components. We looked at the pyrheliometer, pyranometer and unshaded pyranometer, and we also looked at one major phenomena which can impact the solar radiation intensity under different conditions, which is the cloud cover. And we saw how cloud cover has a very direct and very impactful linkage on the radiation intensity. Then we looked at this another way of quantifying solar radiation in terms of energy per unit area per unit time, which is solar insolation, and the measuring device used for solar insolation, which is the Campbell Stokes recorder. So, in the next lecture, we will be looking at some of the standard solar radiation data sets and the concept of TMY, or the typical meteorological year. So, thank you for joining us today. Hope to see you in the next lecture. Thank you.